Okay, so basically, what all things we have seen in three phase. We first of all compared this three phase with a like how single phase is different than a three phase system. So we found out various relationship in this, and why we are using this three phase system. So we started our discussion with this part. Okay, so there was like transmission. So in transmission part, this is mainly used, and based on the size and based on the voltage regulation part, and we can supply to domestic and industrial purposes. Wherever we need larger amount of power application, we use three phase. Okay, and we'll be studying in module 4 about the rotating magnetic field. So in that we'll see like how a three phase induction motor is self starting. So these all things we have seen. So here basically my three phases are 120-degree apart from each other when I'm talking about a balanced three phase system. Okay, so we can represent them in polar form, that is magnitude along with its angle, and we can also use J operator to represent any of these three phases, and we can have mathematical operation on them. Then we have identified that the resultant of all three voltages which are 120-degree apart, and if we consider them as phase A, B, or C, and usually in general practice in electrical engineering we use R, Y, and B phase. Okay, so when we add them, finally we get resultant as 0. Okay, so this is very important. So this is regarding generation, where we have a magnetic field and we'll be rotating a coil or winding. Okay, and as per its orientation, we can generate a three phase voltage. Now these are the two basic connections we have in three phase. So this we are talking in terms of load. So a load can either be connected in a star or it can be connected in delta. Okay, so since we have a star and delta connection, so we should also understand this, that if all the similar points, that is, if all the ending points here, for example, I'm just giving you an overview and finally I'll cover like complete this part. So, okay. So if this is start, so I'll represent start with S, and if this part, another one is finish part of this winding. Okay. So, and I'll represent this with F. So suppose this is also start and this is F for Z2, and this is also start and this is F for this Z3. So you can see that all finishing points are connected to a same point. So this kind of connection is known as star connection. Okay. Whereas suppose if this is the start, this is finish, this is the start, this is finish, and this is the start and this is finish. So you can see here, when starting point of one phase is connected to the finishing point of another, and finish starting of one is connected to finishing of other. So when load is connected in this way, this kind of arrangement is known as delta connection. Okay. So here in this diagram itself, I can show you, but okay, let's move to another part. So when we talk about balanced load, it is very important that they are this condition that the loads Z1, Z2, Z3 can either be star connected or it can be delta. Okay, so three phases can be used independent of each other, supplying power to different loads. Okay, we can use this for domestic power also. So if three phase load, if all the three impedances are equal, both resistive as well as the reactive parts, that means R plus jx, suppose this is my impedance. Okay, so it is saying that both R and this inductive reactive part should be equal. So that kind of load is known as a balanced load. So you have to also consider this point that if a balanced three-phase supply is applied, the current will also be balanced. That means if I have V at an angle 0, V at an angle 120 degree, and V at an angle minus of 120 degree, therefore I'll have I at an angle 0, I at an angle 120 degree, and I at an angle minus 120 degree. Okay, so when we are talking about balanced load, this condition should be fulfilled. Okay, so this is one part. Now the same thing that I told you, R and R dash are start and finish point. This is phase R, this is phase Y, this is phase B. Okay, so you can see here your finishing point, all the finishing points are connected together, this line. Okay, all this is connected together. We call this, since all these points are same, so we can call that with a name N. So this N is your neutral point. Okay, so this is your neutral point. Now you can see your starting point going to a load. So this is your three phase winding connected in star. So when we are talking about the load, okay, so you can see the start point is going to this part of the load again. So starting point going here and ending points meeting together. So this type of connection is star, or you can call it as Y or inverted Y. Okay, so these all points are same. So if we can draw wires from all these three phases first, that is R, Y and B, and we can also draw a wire from this which we can name as neutral. Okay, so these are the lines. What statement I used, we can draw lines from these, we can draw wires or we can draw lines from these parts. So these all are lines. Okay, so whatever is the voltage between, sorry, so what I'm trying to say here is, so whatever is the volt, so I mean to say whatever is the voltage between these lines. Okay, or I'll draw it more clearly. Next diagram, I'll just show you here. Okay, so suppose I'll take like this inverted Y, I'll take. Okay, so what I said, I can draw lines or I can draw wires out of these three phases. Okay, and this is my neutral point. So I can draw a wire here as well. Okay, now if this is your R phase, so let's call this as R, Y, and B, suppose. Okay, so between the lines, that means R and Y, I have a voltage. Okay, and between Y and B, I have a voltage. Okay, so this is one voltage, what I can call R, Y. I can call this as YB. So what is left now? There is one voltage between R and B also. So this voltage is VRB. So whatever is the voltage between them, that is nothing but your line voltage. So now what about the phase voltage? Whatever is the voltage, suppose this is your R phase, this is your Y phase, and this is your B phase. So whatever is the voltage between your R and neutral. So this is your suppose VRN. So this is one voltage. Okay. Then between your Y and N, there is one voltage. So this is also in between the phase. So this is V of Yn, and we have also a voltage between B and N. So suppose this is that voltage. So this is Bn, or voltage between this. So these voltages that is occurring across this windings, these are nothing but your phase voltages. Okay, so this you have to remember, like what is my line voltage and what is my phase voltage. And I have to identify a relation, that is what is relationship between my phase voltage and line voltage. Okay, so it will be governed with a constant value. So what is this constant value? This we have to identify. Now, okay, so this is regarding star connection. Okay, so I'll just show you why this drawing is not going. Okay, okay. So, so when we talk about this one, okay, so this is just the same thing. What they have done, they have used a common point N, this one neutral, and they have connected all R dash, Y dash, and B dash at the same point. So the remaining point is R, Y, and B now. So that R, Y, and B, we can take wires from them. So you can see here this wire, this Y, and this B. Okay, and we'll also draw a wire from neutral. So now you can see that there is a load connected between R and neutral, between Y and neutral, and between your B and neutral. So these are the load that is connected in this star connection, and this R, Y, and B, these are nothing but line conductors. Okay, so this you have to remember, so that when you calculate the voltage between these line conductors, you can directly identify that this as your line voltage. And if you have identified your line voltage, you can directly go to this Y dash and Y, whatever is the voltage between this point Y and neutral is nothing but your phase voltage. So it is very important to understand what is line voltage and what is phase voltage. Similar is the concept for line current and phase current. Whatever whatever current is passing in the line is nothing but your line current, and whatever current is passing in the phase is your phase current. So if you look in this diagram here, if you look into this diagram carefully, okay, so you can see here that if suppose if this is my line, this is your all three of them are nothing but line conductors. Okay, so the voltage between them is nothing but my line voltage. All this that I marked with black. Okay, so these all are nothing but my line voltages. So if in these lines I have current, so that is nothing but my line current. Okay, so if this is I, okay, so this corresponds to my line current. And I told you like these are the three phases. So current passing through them. So I'll use a different color so that you, okay, so that you can identify it. Okay, so this one is your phase current. Okay, this I have done for this. Similarly, I can go for, like suppose here my current is flowing in this way, this one. So this is again IPH, and again if it is going like this is again IPH. Okay, so these three are my phase current. Okay, and this one is the line current. So if you look carefully, all these line current values, if I am taking the all of them, so all these values, they all are equal to the phase current. So here the direction should be like this. Okay, so this should be like this. I should use blue here. So you can see here all current coming inwards. If for example, so this is all those line current is exactly same as my phase current. Okay, in this connection. This will not be case in case of delta. Okay, so delta and star, they whatever relationship will find out. So that is opposite. Okay, so if this is my condition, okay, now so again I have Im sine of omega t, Im sine of omega t minus 120 degree, Im sine of omega t minus 240 degree. So I know that in a balanced condition, if I'm calculating the resultant I, so I know that I have to add IR, IY and IB. Okay. So when we add up Im sine omega t minus 120, omega t plus 120. So we have this term Im common and these three terms I have. Okay. When we do this analysis, we found out that this value is 0. So resultant value comes out to be 0. So this is one condition for my base analysis. Now you can have a supply or the generating end and you can have a load end. Okay. Now if you look here, this is star and this is also star connected. Okay. So we have four options overall. It can be either star star, it can be star delta, it can be delta star, or it can be delta delta. So these four connections is possible if we are using star and delta connection. Okay. Now, so and one more thing, this is your supply side and this is your load side I'm talking about right now. Okay, so this you can see this is your star star connection. Okay, so let's see this. Okay, now this was about the star connection. Let's talk about delta a bit and then we'll go to for the comparative study between star and delta. Okay, so okay, so this is start, this is finish, start finish, start finish for your R, Y and B phase. Okay. Now you can see here your finishing point, your starting point, your finishing point, starting point. That means finish of R is connected to start of Y and finish of Y is connected to start of B. So when we'll draw this, it will be something like this B point, B dash point is now again going to your starting point. So start, finish, again start, finish, and this finish is again connected to your start point. So these all points are start. Okay. So this way, when we do the arrangement, it turns out to be in form of a triangle where you have these start and finish, start and finish, and start and finish connected to each other. Okay. Now I can draw wires or I can draw lines from this B, from this part that is R, Y, and B. So these three are nothing but my lines. Okay. So this voltage between these two lines is nothing but my line voltage. Okay. So this is also my line voltage. And overall from R to B, if I have a voltage, this is also my line voltage. So these three are the line voltage. Now, if we look into the phase part, I told you that the between the windings, what is my voltage? So if you look carefully, let's talk about this R dash and this R and Y. So this is something like this. Okay. So this is my R and this is my R dash. This is the point from which a wire has been taken. So all points are same, that is R. And from here, it is going like this and it is mentioned over Y. But all points are same here also. So whatever is the, and this is nothing but my line voltage. Okay. So whatever is between these two lines, the same voltage is in the phase also. So here my line voltage and phase voltage are same. Okay. So in case of delta, VPH is equal to VL. Okay. So this is one condition that we can see, but okay, but so let me clear this and now tell you. So these are the lines. So let's suppose this is my current. So in lines, whatever current will pass, that is nothing but line current. Okay. So this is line current, this is line current, this is line current. So let's suppose this is I of R, I of Y, and I of B. Okay. So if you look carefully, suppose at this node, okay, this is the value of current passing through, like it is showing like this is the orientation. Okay, so if this arrow corresponds to a current or the phase current, let's say this is I phase R, IPR phase current for this R winding. So left, let this is going like this, and this is coming, so this is also current, which is phase current for this B phase. Okay, so my this I line current is equals to, okay, so this is suppose node A. Okay. So what is incoming current in node A? What is incoming current in node A, students? At this end, what is incoming current?
IR, sir.
Hmm?
IR.
IR. Okay. Anyone else? Incoming current?
Sir, IR and IP.
IPR, right? IR and
Yes,
IPR.
IPR.
So that is my incoming current. So I can add up incoming currents, that is IR and IPR. What is my outgoing current here? What is my outgoing current here? Juhi, Juhi, can you tell me what is my outgoing current here in this node A? So it is nothing but
So IP.
IPB. Good. So this is IPB. So this is what, which law? What we are talking about here, which law?
KCL, sir.
KCL. Okay. So we can see that here we are having three nodes and we can apply three KCL equations here. So we can see here that this IPB and this IPR is nothing but my phase value of current. Like they are phase currents. Okay. I'm talking about this IPB and this IPR. And this IR, we have seen here that this is the current passing in the line. So this is my line current. So you can see here on on analysis of this, we have to find out a relationship between my line current and my phase current. Okay, so you can see here in case of a star, we have seen that the phase current and the line current value were same. But in this case, it will never be same because here we are having more than two components. So they cannot be equal. And we'll deduce that what is exactly the value of that particular part is. Okay, so this is one thing. Now let's move. So again, we have identified ER, EY, and EB. They are separated from each other by an angle of 120 and 120 degree each other. So they are nothing like, but they are like this. So if this is my ER, this is my EB, and this is my EC. So it will always be associated with a magnitude and direction. So magnitude maximum value we are taking same, but the with angle corresponding, so it is 120 here and it is 240 here. And if I can go this side, this is 120. Okay. So it depends on which direction you are taking, whether clockwise or anti-clockwise. So depending on that, you can write the value. Okay. So finally, we are getting here also the resultant at 0. So that means this is a balanced system we are talking about now. Now suppose voltage and current relationship in a star connection. Let's see this. Okay. So it is very important that you understand this, that if this is your generator, so I'll be sending the value of current. So let's suppose IY current is passing through this phase and it is passing through the line also. So we can see that the same current will follow here. Similar is the case of this IR. The same IR will be passing through this line, which is passing through this phase, and same IB is passing through this line, which is passing through this phase. So this part or this part or this part. Okay. So whatever I have drawn using this one, this is nothing but your phase. Okay. This part. These all, whatever voltage or current will be there, they are nothing but their phase voltage or phase current. And these are nothing but your line conductors. It is mentioned over here. Okay. So whatever current or voltage I am having here is nothing but my line voltage or line current. Okay. And this is your three-phase load. Now this three-phase load can either be in star mode or it can be in delta mode. Okay. Now, so when we apply Kirchhoff's voltage law, so on applying Kirchhoff's voltage law, what we are exactly doing is whatever is my voltage in phase, I'll take that voltage as VPH. Okay. Now VPH, if we compare start with R phase, it is VPH at an angle 120 degree. Okay. So VPH at an angle 0 degree. We'll start with R phase. When we go to Y phase, it is VPH at an angle minus 120 degree. And when we'll go to the B phase, it is VPH at an angle of 120 degree. So one is apart from 120 and another one is apart by 240, which can be written as minus 120. Okay. So if you see here, VRY is VRN minus VYN. So what you are doing, you are subtracting these two voltages, that is VPH, that is R phase voltage, and your Y phase voltage. When you will subtract these two values, you will get the voltage between R and Y, that is voltage between the lines. Okay. So when we are doing by applying Kirchhoff's voltage law, finally, we are left with VPH. So this minus 120 degree, suppose this is in terms of V at an angle theta. Okay. So when we do this, we can write this as V of, this is theta. Okay. So we can write this as V of cos theta minus J sin theta. Okay. So we can use plus sign here for general notation. V of cos theta plus J sin theta. So it is written over here as V of minus 120 degree. So what I can write for this, V multiplied by cos of minus 120 degree plus J sin of minus 120 degree. Okay. Now cos of minus theta is always cos theta, and sine of माइनस थीटा क्या होता है साइन ऑफ माइनस माइनस थीटा एनीवन व्हाट इज साइन ऑफ माइनस थीटा minus sin x, so minus sin theta, correct? Yes, good. So it is minus theta, so we'll replace this value with minus j sin 120 degree, and this will be same it is, so that's why it is cos 120 minus j sin 120. When we do this analysis, we are finally, I'll just clear this so that you can see clearly. Okay. Mm. So we are left with this one. Please try to see this one. That is VRY is VPH root of 9 by 4 plus 3 by 4. But before this, we are getting here VPH equals to, VPH multiplied by 3 by 2 plus J root 3 by 2. So this is the value you are getting for VRY or for line voltage. Okay, you can write it as line voltage. Now your VPH is common term here. So this 3 by 2 and j times root 3 by 2. So this is in the form of like you are having a j operator. So constant plus j times imaginary part. So if I want to go for the calculation of magnitude, so this is in term of this like a plus j of b. So my magnitude of this form is always equals to root over a square plus b square. Okay. So when I do this, 3 by 2 whole square plus root 3 by 2 whole square, that is okay, I'll write it. So root 3 by 2 whole square. So this is nothing but your 9 by 4 plus 3 by 4, 12 by 4 or 3. Okay, so this root of this, so we are doing this, so we have to take root of these values. So finally you are getting root 3 here. So instead of this, what I can write that V line is nothing but root 3 times VPH. Okay, so this was this part. Now, also you can remember this point as if this is A plus J times B. So magnitude I just said is nothing but root of A square plus B square. And if I want to know the angle between this A and B, so this angle is nothing but tan inverse of the imaginary part upon the real part. So here my imaginary part is root 3 by 2 and my real part is 3 by 2. So 2 cancel, root 3 by 3, 1 by root 3. So this is nothing but tan inverse of root 3. No, 1 by root 3. So here your theta is coming out. When tan inverse of 1 by root 3, students, what is the value of theta?
Thirty degrees, sir.
Hmm. Okay, sin theta, cos theta. So tan is division of like sin theta by cos theta. So 0, 1 by root 3, 1 root 3 not defined. Okay, or infinite, whatever you say. 0, 30, 45, 60, 90. Okay, so you can see here what is 1 by root 3 here when at what angle? At angle 30 degree. So that's why here theta is nothing but 30 degree. We have calculated this value as 30 degree. We are not doing that angle bisector method to find out that. That is known as geometrical analysis. Okay, so if we can get for this phase like between for this line voltage Ry, so for other one also we can calculate similarly and we can get same result, that is root 3 times VPH, and that angle value is also associated with this. Okay, so finally we can write that my load voltage line voltage is always equal to root 3 times VPH. Very important exam perspective. Okay, so now this is regarding the geometrical analysis. So here what we do, we just like for example, you don't think about this one and this part, you just think about this. So this VYN is taken in this side. So this is minus VIN. This is added with your VRN. Okay. And to get the value of VRY. Okay. So, okay. So for this, what we can do, okay, I'll show you the base diagram here. Okay. So we have discussed that, but still, if you want, I can show you. Suppose this is your VRN, okay, and your this is your VYN, and this is your VBN, okay. So they are 120 degree apart from each other. So what I am doing, I am taking this VN in this side. Okay, I'll use black. Okay, so I'm taking this in this direction. So this is my V of minus V of yn. Okay, so this is this direction. So what I'll do, I'll take a parallel line here because I'll be using a parallelogram vector addition using parallelogram. Okay, so I can connect this. So when I'm doing this, initially this total amount, total angle was how much, students? Between R, Y and B, what is the angle between any two of them? 120
120.
degree. Okay, when I intersected this, so this will divide this this angle equally. So this is your 60 and this is also your 60 degree. Okay, as of now. Now again, I have this parallelogram. Okay. So now with this, I can have a resultant vector. Okay. So this resultant vector, I'm calling it as VRY or the line voltage. Okay. Now again, this 60 degree, I'm cutting equally, angle bisector is there. So I'm cutting this equally. So now this angle is coming out to be 30 degree. So while doing the geometrical analysis, we are finding out the angle, like exactly what is my angle. So in this, for example, this is your A. Suppose this is your A, this is your B. Okay, and this is your resultant R, and this is your angle theta. So what is your resultant? Can you tell me very fast? A square plus B square plus 2AB cos of theta. Okay, so for example, this is my VRN, this is my VYN. Okay, so magnitude is same here. So let's take magnitude as VPH. Okay, so it will be VPH square plus VPH square plus 2 VPH into VPH into cos theta. Cos theta is what? 30 degree. So cos of 30 degree. So this entire thing is coming under root. Okay. So 2 VPH square plus 2 VPH square into cos 30. What is cos 30, students? 2 VPH square plus 2 VPH square into root 3 by 2. Okay. Cos 30 root 3 by 2. All of you?
Yes, sir.
Okay. So this 2 and
Yes,
2 will get cancelled. So what we are left with? Uh, just a moment.
Sir, 2 is common.
Which one?
2
2
should
is
be taken.
common. No, this one. 2 into VPH. 2 into VPH into VPH into cos theta we have. No. Students, we are doing anything wrong here? 1 minute. 0, 1 by root 2. No. We are doing some mistake here. I think we are doing something. Okay, sorry. When we talk about this A and B, there the theta is not between resultant and this. Theta is between A and B. Always remember this part. Theta is angle between A and B, this cos theta. So what is my angle between Yn and VRN? The angle is 60 degree. So here I should place here 60 value. So what is value of cos 60? It is 1 by
1
2.
by 2, sir.
Okay. So this is 1 by 2. So this 2 cancel. So this is 2 Vp square plus Vp square. So this is 3 Vph square. Okay, VPH will go outside. It is square of square root, so it is VPH, and we have this root 3, which is equal to my this resultant value, which is nothing but my line value. Okay, or I can say this is as line voltage. So that is how we can prove this part, that my line voltage is always equal to root 3 times my phase voltage. Phase voltage. Okay. So this is one part, very important. Okay. Now this is delta connection. Okay. Now your generating end is in delta connected. Okay. Now this is current going through this line. So this IR, IY and IB are my line currents. Okay. And this IB dash B, IR dash R and IY dash Y, these are nothing but my phase currents. Why? Because they are passing through phase. So you can see here the same current, it is passing through, sorry, the same current. If you see, this current is going in this direction, this is coming downwards and this is going outside. So one incoming current, if we consider this particular part of the circuit. Okay, so if we consider this node, so here one is incoming and the other two are outgoing. Okay, so we can say that there is some relationship between phase and current, phase and line current, but it is not equal as it was in case of star connection. So let's see. Now this is a three phase balanced load. This is again, it can be a star or it can be a delta. Okay, so this you have to remember now. So when we do this analysis, okay, so here we'll be using KCL. Okay, in delta connection, we'll be using KCL. So here also the approach is same. Like suppose for your R phase, for your Y phase and for your B phase, you are having like 120-degree apart relationship. Okay, minus 120. So these are for your R, Y and B, suppose. Okay, now you need to have a resultant out here. So as you can see here in this part, I'll just for IR they are doing. Okay, so we'll also do for IR. So this part. Okay, so this is outgoing, this is incoming, this is outgoing. So incoming is IR dash R and outgoing is IR plus IB dash B. So what can I write for IR, which is my line current, as IR dash R minus IB dash B. Okay, so this one I know in terms of line and phase. Now see here, the same thing they have written here by applying KCL. Okay, so when they will do the analysis, exactly same thing. Okay, two vectors and how to add those two vectors, exactly same thing. When we'll find out that the line current is nothing but root 3 times my phase current. Same concept you have to apply. Vector addition of, did I spelled it correctly? अरे नो सर तो बोल दो कम से कम. Okay, so this is your relationship between line and phase. Okay, and here my voltage and voltage of line and voltage of phase is same. Why? You can directly go to the diagram here and see, this is between two lines. So whatever is this is nothing but my phase voltage. Okay, now I told you voltage in the winding or voltage in the phase is nothing but phase voltage. So sorry, this is your line voltage between the lines and this is between your phase. So you can see here all points are same, these all points are same. Okay, and I can use a different color so that you can identify, and all these points are same. So you can see that same voltage will appear between this yellow and this red, between these. So whatever is the voltage across phase is the voltage across line. So your line voltage is same as phase voltage. Any doubt? Anyone, any doubt? Please ask. Okay, so now some of the important points. Okay, for a three-phase system, unless otherwise mentioned, it is in normal practice, the value that is given is nothing but your line voltage or line current. So for example, a three-phase 11 kV circuit is carrying a current of 500 amperes. That means here they are saying that line current is 500 amperes and your line voltage is nothing but 11 kV. Here K is small and V is capital. Okay, and this corresponds to 11,000 volts. Okay, so this is one normal practice. One can calculate the phase voltage and phase current depending on whether it is a star connection or delta connection. Now the current in any phase can be determined by dividing the phase voltage by its impedance. That is, I phase is equal to V phase divided by Z. Okay, and this Z, if this is usually given in numerical problems, so we are doing qualitative analysis, so don't worry about the numerical problems much. Okay, the power factor of Z is same cosine of phase difference between VPH and IPH. Okay, we'll see this. Okay, now just 5 more minutes, we'll complete this part. Okay, so this diagram they're talking about, no, before that. Okay, okay, let's suppose I have told you that in a three-phase system I'm having three windings. Okay, it can be A B C or R by B. We are doing this today by R by B, so let's take it as R by B. Okay, now when we talk about power delivered, okay, so for any AC system it is nothing but VI into cos of phi, where phi is angle between voltage and current. Okay, so for one winding this is the value, for second winding this is the value, for third winding this is the value. So overall total power will be nothing but at y, at r by b, r, y and b, so it will be same. Okay, so vi cos phi plus vi cos phi plus vi cos phi, so it is nothing but 3 times vi cos phi. Okay, so this is about the total power. We are talking about instantaneous power. Okay, now when we are taking these powers, we are taking VPH and IPH into cos phi. So we are talking about phase voltage and line voltage. Okay, now what is the relationship between let's take first example for star. What is the relationship between phase voltage and line voltage? Okay, so anyone?
So they are equal.
Star, for star connection. Anyone?
The line voltage.
I can't hear you. Your voice is breaking.
Sir, the line voltage is root 3 times the phase voltage.
Sure. Star line voltage equal to root 3 phase voltage. Okay. So, line voltage is equal to root 3 phase voltage. Now, can I replace my VPH with VL by root 3? Okay, and what about line current and phase current? What is the relationship? Anyone for star connection?
So
So
for
it
the
is same.
line,
Correct? Yes or no?
yes, sir.
Okay. So, when we are doing this, so can I replace my VPH with VL by root 3? Okay, so you can write over here. Sorry. So you can, what happened? So 3 multiplied by, sorry, something went wrong here. Okay, I'll use one more new one. So if power is equals to, I don't know, something went wrong with this stylus, why it is, power is 3 VPH multiplied by IPH into cos theta. Okay, so I'm saying that this I can write as VL by root 3 into IL into cos theta. So here power I can write in terms of root 3 VL IL cos theta. Okay, so this is for star connection. Now what about delta? Okay, can you tell me what is relationship between these two and these two? Anyone? Come on, fast. I know it's your lunch time, but I won't take 2 or 3 minutes more. Tell me. In delta, what
Delta,
is the
sir, the
relation?
voltage, it will be equal, sir.
Very good. So
And for current, IL will be equal to root 3 of phase current.
root 3 of phase current. Okay. So IL by root 3 cos theta. So again, this will be, power will be root 3 VL IL cos theta. So you can see the power is coming out to be same here. Okay. So same thing is mentioned over here in your PPT. Okay. So this I have to move just a minute. Okay. So this is your total instantaneous power, that is across three phases, PA, PV, PC. And when we take the average power, that is either PA or PB or PC. So it is coming like we can draw PA, PV, PC in terms of their 120-degree apart from each other. So it will be coming somewhere in this part. So you can see that total instantaneous and average power, you can plot this like this. Okay, and here this has some problem. Okay, so here it was mentioned like individually what is the value and total power how we can replace. In case of star and delta, we are getting this as my power. Okay, total power root 3 VLIL cos phi, or in total you can write 3 times VPH IPH cos of phi. So this is one thing. So finally, star connected system, similar ends are joined together. Okay, so similar ends are joined together. That means, okay, so this start finish, finish start, finish start. So similar ends are joined together. Here dissimilar ends are joined together. That means start, finish, finish, start, finish, start, finish. That means finish and start. Dissimilar ends are joined. So this is delta. Here we have identified that VL is equals to root 3 VPH and load, line current and phase current is same. Here your line and phase voltage is same, but current is having the same relation as we were having for the voltage in case of star connection, that is root 3 times IPH. Here a neutral wire is available. This is your neutral wire, but here there is no neutral wire. Okay. Now this is a 4-wire 3-phase system. How 4-wire? 1, 2, 3 and fourth one is neutral. So 4-wire 3-phase system is possible. Here we cannot have this 4-wire system. We can only have 3-wire system. Okay. It is used for both domestic and industrial loads. It can handle this star connected system. This delta connection is used for higher power application, that is only industrial load. Finally, by earthing the neutral wire, relays and protecting devices can be provided in alternator for safety. So here, because of this neutral wire, we can actually provide safety devices or safe protecting schemes for any of these connections. Okay, because we can short this neutral wire, whereas we can earth this neutral wire. Whereas in this case, we don't have neutral wire, so we cannot use relay. Actually, this is a protecting scheme, relay or any protecting device in case of a delta connected system. So this is a comparative study which will help you to remember these relationship, and you can write these points if they will ask you something about star and delta. So finally, everything we have covered, like 3-phase systems best suited for high for transmitting high power efficiency. Okay, and also providing powerful motor devices. So we are talking about industrial application. Okay, always remember 3-phase higher power industrial application. 3-phase systems, we mark them as red, yellow, and blue, or RYB. You can say ABC, 1, 2, 3, anything. They can be connected either in star or in delta. The voltage across the current through the components of the load or source are termed as phase values. Okay, VPH or IPH. The voltage between supply conductors and current in these conductors are nothing but your line values. Okay, so this is your definition for line and phase. Okay, in both star and delta, line voltage are mutually displaced by 120 degree. Okay, normal practice, we use line voltage or line current value. Sum of line current is always 0. Okay, if load is balanced, we can multiply by 3 and we can do this VPH IPH into cos theta. Okay, finally 2 watt meter is a method by which we can measure the total power of a 3-phase system, and this is the formula. Okay, so this is watt meter 1 reading, this is watt meter 2 reading. So if we can do this, we can find out the angle between that particular arrangement of 3-phase system. And for star connection, this is the relation. For delta, this is, and total power or any balanced load, this is the relation. Okay, so we'll be using this point. Finally, you can use this as your reference for star load. Okay, where your line current is equal to phase current. Okay, and your line voltage is not equal, but they have a relation root 3 times root 3 times phase voltage at an angle plus minus 30 degree. Okay, so this is your VAN. Okay, or you call it as your phase voltage. Okay, and this is between lines. Okay, VAB. So you call this as line voltage. Everything is given here. You have to just look into it and you have to identify. And this is for your delta. Current is coming like this. This is the orientation of current. So we can know that the current, load current and phase current won't be equal. They'll be having some relationship, that is root 3 times VPH. And here your phase voltage and your load voltage, line voltage, both are coming equal. Okay. So this was about 3-phase system. Okay. So now we have completed second module completely. From tomorrow, we'll be starting transformers. So it has much theoretical weightage than numerical. So we have to get into the concepts and we have to make sure that we understand it well and we can then complete that part also. Okay. Any doubts, anyone? Okay. Thank you very much. Bye. Take care.
Thank you, sir.